Well, hello again, Mr. Bucko back with another triangle. This one is a 30, 60, 90 triangles we're going to talk about here. But as you can see, there are actually three different triangles on the screen. So we're going to kind of sort this stuff out and talk about how 30, 60, 90 triangles come to be and the relationships of their sides and all that fun stuff. So let's start here with the triangle that I have. And I have a triangle ABC. This kind of bigger triangle. This triangle is an equilateral triangle. And I know that it's an equilateral triangle for a couple reasons. Reason number one is I measured the angles, angle A here, angle B right here, and angle C right here, and they're all 60 degrees. Here's angle A, that's the measurement there. Here's angle C, there's the measurement there. And then here's angle B. So this is an equilateral triangle because they're all 60-degree angles. And if you don't believe me, then I even measured the side lengths. Side length AB right here is 10.68. Side length BC is also 10.68. And side length AC is also 10.68. This is an equilateral triangle, everybody. And here's the proof of that. Three 60-degree angles, and all three side lengths are the same. So I'm going to move these out of the way. We have an equilateral triangle there, no doubt about that, and those values will always stay the same once I manipulate this triangle and get these things out of the way. So you'll notice that if I change the size of this triangle really small, it's still equilateral, still all 60-degree angles, side lengths are still all the same. I want to make it bigger, still 60-degree angles, still three side lengths are the same. Can move this one too, can move it way over here. Still 60-degree angles, still three side lengths that are the same. So in any event, this is an equilateral triangle no matter how I manipulate that thing moving forward. Now I have this segment BD. Now BD is an interesting segment. This segment is several things. First, it's the line of symmetry of the equilateral triangle. It's also the angle bisector of B, and I have evidence of that because I measured the angle right here, DBC or CBD, how did I name that thing? Right here, DBC, this angle is 30 degrees. The whole thing was 60, so therefore this segment is a bisector of this taller angle, or this top vertex angle. That's a better term right now, sometimes a vertex angle, but it's an angle. It's 30 degrees cut in half right here. And then this angle C is exactly as it was. That's still 60 degrees because that's not touched. And then down here, a 90-degree angle is formed. So what I have here is a 30, 60, 90 triangle. So going back to this segment here, the segment is a couple things. It's the line of symmetry of the equilateral triangle. It's also the bisector of this angle B because it's now we have a 30-degree angle right here. It's also, just as important, perhaps more importantly, it's also perpendicular to this segment down here, hence the 90-degree angle. And it's also the bisector of this side length AC. And I have evidence of that because AC is, in this case right now, 12.20 centimeters. And then if I take DC, this length right here, that's 6.1, which is exactly half of this. So therefore, this one has to be 6.1 as well. So this line segment right here is very important. It is the angle bisector and the perpendicular bisector of the angle and the side. So what's happened here, why this is so important, is because we've just formed a 30, 60, 90 triangle. So I'll move that back. We have a 30, 60, 90 triangle. And the relationship of these side lengths now, this side length, and this side length are special, which is why it's a special right triangle. So this side length right here, DC in this case, is 6.1. BC is going to be 12.2, still 12.2. That didn't change. And you'll notice the relationship between these two side lengths, in this case of the 30, 60, 90 triangle, the short leg, the shorter leg, because it's opposite the 30-degree angle, is half of the hypotenuse. That will be the case no matter what. And I'm going to move these angles out of the way, and I will manipulate that so that you do indeed believe me. So if I make this triangle smaller, here's DC 4.46, BC is 8.92 now, that's still half. The hypotenuse is always double the shorter leg of the 30, 60, 90 triangle, no matter what. If I make it bigger, we're at 8.06, 6.11, not necessarily half because these are decimal approximations, but hopefully we get the idea there. Then no matter how I manipulate this, make it super small, this is still half of the hypotenuse. That will always be the case. So that's what the relationship is between the hypotenuse and the short leg of a 30, 60, 90 triangle. So that's kind of handy to know. But then there's this side length here. How long is this side length with respect to all these other sides? The side length BD, or the longer leg, because it is opposite the 60-degree angle. So this is the long leg, it's opposite the 60-degree angle. This is the short leg, it's opposite the 30-degree angle. And this is the hypotenuse because it's opposite the right angle. So the length of the long leg is going to be the length of the short leg, in this case, 6.42, times the square root of 3. And I have that right here. DC, the short leg, times the square root of 3 is 11.11 centimeters. And I can verify this because I actually have the software here measure this length. And this length, this BD, is 11.11. And no matter how I manipulate this triangle again, you'll notice that the short leg times the square root of 3 will always be equivalent to this side length here. That's always going to be true. Notice how these two are not changing with respect to each other when I make the triangle really big or really small, or if I want to move things around. You'll notice that those two values always stay the same because the relationship we want to focus on here is that the length of the long leg is the length of the short leg times the square root of 3, which is what we have here. And then we can go back and we can talk about the hypotenuse, and we can say that this is always twice the length of the short leg, and I have that evidence right here. The length of the short leg times 2 is always the same as the hypotenuse. So all those things are there. I have this value right here. This is the Pythagorean theorem saying that a squared, in this case the short leg, plus b squared, in this case the long leg, equals, and then we have a value, which turns out to be the same thing as c squared. This is the hypotenuse squared. And now you'll notice that no matter how I change these values, these always stay the same because that's the Pythagorean theorem. So that's what a 30, 60, 90 triangle is. The big thing is short leg is, let's call it x. Can be whatever. As a result, the hypotenuse is 2 times x, or 2 times that value. And then the long leg is going to be the square root of 3 times x, or times the short leg, whatever that value is. That's going to be the length of this. So if we know the length of one of these sides, we can find the lengths of the other sides because of these relationships that I have highlighted.